Hey there everybody, and welcome to my lesson on differentiation using tables or a graph that's been provided for you. This is going to be a lesson where we're going to be identifying an approximation of the derivative based off of things that are given to you in a table or on a graph somewhere. So we've seen things like this previously, but this is where we're going to start incorporating other things that we've seen with differentiation techniques, as far as maybe the chain rule, the product rule, or the quotient rule, to kind of build off of the idea that, okay, well, even if we can't necessarily get the exact derivative with the data points we have, we can at least get an approximation. So that's what we're going to be taking a look at today, and here's our first example. We have this table that's, we have no idea what the function is, but it's asking us, we know it's differentiable, it's asking us to find the derivative at the end point. It's asking us to find the derivative at the very beginning, which, okay, we can do that. Normally what we would do is, if we're trying to take the derivative of a point on the table, like what we're doing here, we want to find f prime of 0.1. We would kind of take the points to the left and the right of it to approximate it. Unfortunately, we can't do that here, so we'll take the point itself and the point immediately after that, and we'll just do our normal difference quotient, the slope formula, to figure out what that's going to be. So here we'll say f prime of 0.1 or 0.10, however you want to think of it as. And, the change in y will be 0.433 minus 0.261. And the change in x will be the 0.2 minus the 0.1, giving us in the numerator 0.1172 over 0.1. So the final derivative, we would look at it as being 1.72. And again, it's just an approximation based off of the points that we have in the table. So there we go. That's how we're going to be looking at that one. Just normal slope formula between some points on a graph. So here, this is where we're going to start seeing some things that we would have done. I don't know why I'm there. I don't know why the table was outlined the way it was, but now we're given a bunch of points on a table here with two different functions. We have function f and its derivative, function g and its derivative. And what we're being asked to do is, can we find the values of a composite function? So what they're telling you, for instance, in part A, they're telling us, and let me see if I can make, I'm not sure how it's going to look on the video that when you guys are watching it. But let me just see if I can squeeze a little bit more space here, so that way we can fit it all on one area without having to move anything. So h of x, you can see, is a composite function of f of g of x. So that means h prime of x, according to the chain rule, is going to be the derivative of the whole function f prime of g of x multiplied by the derivative of the inside g prime of x. And in this case, we're being asked to evaluate it. If you see here, it doesn't tell you, does it? But in your notes, what it's telling you to do, it's telling you to evaluate it at x is equal to 2. So that's what we're going to be evaluating it at. Maybe, did I cover it up? Nope, it sure doesn't. At x equals 2. That's what it should say in your notes. So hopefully, anybody that's watching this understands that we're evaluating this at 2. So here I'm going to say h prime of 2 will be equal to f prime of g of 2 times g prime of 2. And we don't have to actually figure these out. We can pick these values directly from the table as it was given to us. So f prime of g of 2, g of 2 in this case is going to be a 3. And g prime of 2 in this case is going to be a negative 1. And so now I need to look at the table and see, well, what is f prime of 3? And that works out to be a negative 2 times the negative 1. So h prime of 2 is 2. And now we'll do the same thing for example B here, where again we're evaluating it for x is equal to 2. Let's pick a different color here. So based on what we see here, k prime of x, to find its derivative, again we have to use the chain rule. So we're going to take the derivative of the whole thing, which would be 3 times f of, and we can kind of put this in parentheses here, f of x squared multiplied by f prime of x. So that's what k's derivative will be. So here we're going to say k prime of 2 will be equal to 3 times f of 2 squared times f prime of 2. And let's see what the numbers are from the table. Looking at the table, f prime of, or f of 2, rather, let's look at f of 2 first. F of 2 is going to be a negative 4, so it'll give me 3 times negative 4 squared. And f prime of 2, and that squared looks kind of like an r for some reason. And f prime of 2 is an 8. So 3 times 16 times 8, I would probably just type that on a calculator, to be honest with you. I'm not big on doing big multiplication stuff in my head. That would be 384 in that case. So that's what we're looking at for the, how we're looking at the table. Now those are two examples where we had to use the chain rule for symbolic differentiation using this table. Now, and let me go ahead and, again, let's shrink this guy a little bit so we can try and fit all of our work on one area. Because if you notice what and again, we're still evaluating these at x is equal to 2 for all 4 of these examples. Here, if you notice, we have function p. It's not so much a composition of functions, although part g, if you look at g of 2 of x, that's going to be a composition of functions. So that means not only do we have to do the product rule between the multiplication of f and g, but we also have to use the chain rule when we take the derivative of g. So looking at that, let's go to a new color here just to keep things different. Here, I'm going to say p prime of x will be equal to, so the chain rule, I'm going to take the derivative of f. So I'll say f prime of x. And g will stay the same, times g of 2x. And then we'll add f of x times the derivative of g, which in this case is going to be g prime of 2x times x, because the derivative of the 2x is just x. Nope, I have that backwards. Some of you are probably, no, Mr. Pierce, that's not right. The derivative of 2x would be 2. There we go. Now it looks okay. So now let's start plugging in 2 and see what we get. So, plug in the 2. I just said it, and I wrote x again. So here I'm going to say f prime of 2 times g of 2 times 2. So if you want to just write a 4 there, you can. In fact, let's go ahead and do that. That'll just give me a 4, g of 4. Let's see, and now we're at plus f of 2 times g prime of 4 when I substitute the 2 there times 2. All right, let's see what we wind up getting when we find our numbers by substituting. So f prime of 2 looks like it's going to be an 8. G of 4 looks like it's going to be a 2. And f of 2 looks like it's going to be a negative 4. G prime of 4 is going to be a 3. And multiplied by 2. So 16, and that's going to give me negative 12 by 2 would be a negative 24. So 16 minus 24, negative 8. There we go. And for the next one, it should be pretty obvious that we're going to be looking at using the quotient rule. And in this case, because function f is a composite function, f of 2 of x, rather than just f of x, we're going to have to use the chain rule when we take the derivative of part f. So let's go ahead and start looking at this one. R prime of x, just using the quotient rule, low d high minus high d low over low low is going to give me g of x times the derivative of f, which in this case will be f prime of 2x times 2 again, minus high d low, so I'm going to say f of 2x times g prime of x, all of it over low squared or low low, so this will be g of x quantity squared. And again, we're looking at this for r prime of 2. So g of 2 times f prime of 4. When I substitute the 2, we get 2 times 2 times a 2 minus f of 4 times g prime of 2 over g of 2 squared. All right. And now let's see what we get from our tables. So g of 2, in this case, is going to be a 3. F prime of 4 gives me a negative 1, and that all gets multiplied by a 2. F of 4, in this case, is a 0. And g prime of 2 is a 3 over g prime, or g of 2 in this case is going to be a 3, so we'll say 3 squared. So here we can just see that that's going to just go to 0 because 0 times anything is 0. And this 3 and this 3 squared are going to simplify, so that's going to give me, when I take the product of the numerator, negative 2/3 for my final value of my derivative for r prime of 2. So the last several examples, the last several problems are all kind of referring to this graph where we have somewhat of a polynomial looking function for function g, and maybe a piecewise function with an absolute value and a linear expression for function f. So here we're going to use the same graph, and I'm going to just try to move things along here and see what we wind up getting. Hopefully it's going to work out okay. So let's try taking a look here at g g prime of 3, okay? So g prime of 3 is going to be the derivative of function g when x is equal to 3. Now I don't have a straight edge necessarily. I could pick lines, but those are not as easy to delete just on the fly as erasing something would be. So we're looking for the derivative, oops, I guess it helps if I turn my pen back on. We're looking for the derivative at that point of function g. So we're going to have something that kind of goes this way. Now if you're doing this on paper, I would certainly encourage you to have more of a straight edge doing this, because when I did it with a straight edge, I was able to get this point right here at 5 and 4, as well as the point that's actually on the graph of 3, 5, to basically just do the slope there. And that's essentially what I'm doing is, again, kind of like the table at the beginning of the lesson. We're just taking the point of tangency and something that appears to be on that line of the derivative, or you could just graph the line and estimate what the slope is. But here I'm looking at g prime of 3 to be the difference quotient of those. So I'm going to say 4 minus the 5 over the 5 minus the 3 for the change in the x's. So that works out to be a slope of a negative 1/2. And that all looks, you know, that looks pretty close to what the line that I drew was. All right, so let's clear this off. And now let's take a look at B. Oh, that's not going to work, is it? Let's take a look at B here. So here we have a it's not exactly something where you have to use the chain rule, because it's just asking you to evaluate it at f prime of g of 3. So in this case here, I'm going to just look at the function and say, okay, well, what is function g what is it going to be when x is 3? So when x is 3, so here when x is 3, we get that 5. So I'm looking at this one as f prime of 5. So I want the derivative of function f at 5. What's the slope of a tangent line there? Well, if I look at 5 there, we have that point right there, which is at a corner, meaning that the function is not differentiable at that point. So this does not exist. Let me clean up my graph here. And now let's take a look here at example C. Okay, I think I can, there we go. So C is asking us to find h prime of 3, and it told us on the last slide that function h here is a composite of f of g of x. So we have to use the chain rule at this point for function to find example C. So here we're going to say h of x was f of g of x. So h prime of x is going to be f prime of g of x times g prime of x. And in this case, we're evaluating it at 3. So f prime of g of 3 times g prime of 3. Now g prime of 3, we already got. That was the answer that I'm looking at on example A. So here we'll say f prime. So what is g of 3? G of 3 was 5. And we got g prime of 3 to be a negative 1/2. And we've already actually seen f prime of 5. F prime of 5 was the answer on B, where we said that f prime of 5, oops, not D, we say it does not exist. So anything that, you know, if it's not differentiable at f prime of 5, then multiplying it by negative 1/2 doesn't mean anything. So does not exist is going to be our solution here. All right, so now let's take a look at f prime of 7. So this is very similar to what we just did on example A. We want to go to where function f is 7 and see what is the slope there. Now in this case, we're on a line, and the slope, the derivative, the slope of a tangent line is the slope of the line itself. So in this case, I'm going to just, f prime of 7 is going to be the slope of that line. And I have another point right there. So that one is very easily identifiable to be negative 1/2. And the last two that we're going to be looking at here, let's take a look at E. And let's get some nice color here, something I haven't used. Let's go with this green color here, I guess. So G prime of f of 7. So f of 7, here we're going to say G prime of f of 7. And f of 7 in this case is a 5. So we're looking for G prime of 5. Well, G prime of 5, we're looking here on the function G. We have that guy right there. That's the point. There's G. We want to know the slope of the line there. Now again here, doing it on your notes at home, I would definitely tell you to have a straight edge looking at it. And the points, uh, let's see if I can draw it in here okay. That's about the best I could do without having a straight edge. But when I did use a straight edge, I wound up going through that point right there at 7 and 2. So here I'm going to take a look at the difference quotient between this point here, and we'll go ahead and just call this point. We'll say that that's at 5 and 3.5. So I'm going to do the difference quotient between those 2 points. So that'll give me 2 minus 3.5 for the difference of the y's over 7 minus 5 for the difference of the x's, which will give me a negative 1.5 over 2, which if we simplify that to be just integer values would be negative 3/4. So that's what the slope, or that's what G prime of f of 7 looks like it's going to be. And let's take a look at our last one. Oh, come on. We're looking at h prime of 7. So here we have to use the chain rule again. So we'll say that, oh, turn the pin back on. H prime of x, we already have that right here. So I guess I don't need to write that out again. So let's just go ahead and start doing our substitution. H prime of 7, here I'm going to get f prime of g of 7 times g prime of 7, and let's see what we wind up getting. So f prime g of 7, 7, and here's g. We have that point right there. Now it's not an integer value, and this is one of the issues that we're going to have to deal with here. What is the y value there? So I'm going to just say it's at about 7 and 2.8, because it's not all the way to 3, but we'll go ahead and go with that one. So g prime of, or g of 7, we'll say is going to be 2.8. And g prime of 7, we got that from example E, so we'll use that same negative 3/4 value. Oh, nope, I'm lying. That was g prime of 5, wasn't it? I am not. All right, so what is g prime of 7? So we're looking for the slope at that same point, g of 7. So again, we would want to take kind of a straight edge here and go through it. Let's see, can I? Oh, that's way off. But again, you would want to have kind of a straight edge to help you with it. Oh, that's a little better. But the points that I got when I went through it with a straight edge were this point here and this point here. But if you kept going to so that way you could have like an integer value, I actually got it to go right there at 3,1. I'm sorry, not at 3,1. Golly, let me clean this up and see if I can get a nice. We'll just take a straight edge, an actual straight edge here. So we're trying to be tangent to that point here. Give me my straight edge. What did you do, computer? This is what I had when I graphed it using my straight edge, and that line's a little bit thick, but the points that I used for the slope were right here at 8,3 and right here at 1,1. Although it looks like maybe there's another value that you could have used here at 5 and 2. But we're going to find the slope of that line, which in that case, the slope of the line was 2/7. So now we need to estimate what is f prime of 2.8. So 2.8, we're about here. We're going to come up and we're going to just be on this line segment here. So the derivative of that is going to be the slope of the line segment itself, which in this case, looking at the integer values, looks like that's going to be a -2. So -2 times 2/7, in this case, -4/7. So you can see there's a little bit of margin of error depending on how well you draw your straight lines and what you're estimating the value of some things from a graph could be. But that is going to wrap it up for this lesson on how we're using revisiting finding the derivatives of functions from a table or a graph, but now where we're incorporating things like our chain rule, our product rule, and our quotient rule. So if you have any questions, please you know how to get in touch with me. And until I get to see you guys again, thanks for watching. Take care. Be safe, and we'll talk to you soon.